So I'd like to share with you just a couple of issues of notation that might be interesting to you, that may show up if you're doing any extra reading in this subject. They won't appear a great deal in the instructions that I will give you, but they can show up quite easily if you're looking around. So the first one is exponential notation. And what you'll find that you might have a function that's described as f naught e to the I omega t. If it's an exponential function, we know this is oscillatory. And so we know this is going to be f naught, and that's going to be there could well be damping. Not guaranteed, but could well be there. And we'll use t as our variable. And then quantity cos omega t plus I sine omega t. Now, omega, this is not, I emphasize, a w, but a lowercase omega. Greek letters, like the Latin alphabet that we're using here, have capital and lowercase. So omega, as you may recall, a lot of you familiar with the capital omega, which we use for electrical resistance, and the lowercase is is this form. Now the problem that we face is with with printing and writing is it's hard for us. We're not typesetting things. And we get Greek letters and our own alphabet that are not agreeing. They're very similar, and it's very difficult for us to separate them. You see the same thing with a rho and a P, for example, and an N and an eta, and other ones. But those are the ones that are of a concern. So if you're dealing with oscillatory functions, even not forgetting differential equations, just simple wave mechanics, in your first or second year, please, if you put your hand up and talk about the W on the board, you have lost all esteem your professor might have for you. So be very careful about things like that. That will identify you in a way you perhaps would not want to be identified. Now we know if the function is real, or better still, the equation, let's say, has real coefficients, then our solution is, and then we would have f naught e to the a alpha t, and then cos omega t plus sine omega t, and we can just drop the I altogether, as explained in the previous lesson. However, an oscillatory function, as you know, doesn't look like this. So on my page is posted an example of how this is derived, and you can get to a situation where, and I guess, so we would have something like this, where we have f naught e to the alpha t cosine omega t plus possibly phase shift. And there's a bit of stick handling, of course, that goes in there, but let's not worry about that too much. But this is what the type of oscillatory motion that you expect in these cases. Now, but you're going to see differential equations like this described using complex notation. And you might say, Jay, I don't know what that is, but you do know what it is because we've talked about it. Okay, now I'm not going to do that too much in my course, but if you are on Wikipedia even, or opening up textbooks somewhere, you may well find this type of notation. So this gives you just an insight of what they're trying to say, which is not anything really more than we've already said. The other aspect you're going to notice is when we solved differential equations before, we had something like this. E to the Rx, or sorry, let's say e to the x for now, or e to the Rx plus e to the minus Rx, and there would well be a coefficient or something like that. It doesn't really matter. Okay, but this is a recurrent pattern here. It could be negative and so forth too. And so what we find is that we have something you've probably seen on your calculator. The hyperbolic sine function is e to the x minus e to the minus x over 2. And the hyperbolic cosine is equal to e to the x plus e to the minus x over 2. Now these will be used sometimes on references as well, and the vernacular is sinh and cosh. Okay, you'll hear them talk about sinches and coshes, and you'll wonder what they're talking about, and this is just the way it gets used. There is also hyperbolic tangent functions and cosecants and all the rest of it, but this is what you would expect it to be, which is sinh over cosh. And you're going to get e to the 2x, e to the 2x, and this is going to be plus 1 and minus 1. And so you just have, it's just the old-fashioned, and that's just dividing and rearranging variables, which you don't need, I'm not going to bore you with. A couple other things that are interesting too, is that we have sinh of x minus cosh of x, cosh minus sinh, pardon me. Well, what's that going to equal? Well, we don't have to worry about the 2's, okay? But if we have that, we're going to have e to the minus x. And if we add them, we get e to the x. So these are just little notation things that generally fall out of the solutions to second order equations. This example here would be 1/2 of a cosh, okay? Or a cosh of Rx or whatever, okay? So you can see how that would get done. But it's not going to be used a great deal, but you may encounter it in your literature. You know, your algebra engines will handle these very nicely and may actually produce them. When you solve a differential equation, you may actually get, depending on how you set it up, you may actually get an answer that's in the form of one of these. So this is just a short little aside to make you aware of these properties. Anyhow, hopefully this has helped you. Thanks for watching.